Okay, we're recording, great. So I guess the first thing to start with is the homework. So I don't know. So there's the completing the class determination of the non-abelian Lie algebra from last time. But before that, there was also these problems of, what do you think a subobject should be? What do you think a quotient should be? Et cetera, et cetera. So, with those things in mind, well, does any of the two people present have a guess at what a subobject should be?
I think you said you already read it through, but I guess
Right.
It's similar to a subspace, but it also flows under the bracket. So
Right. Yeah, exactly. So our Lie algebra is a subalgebra. I don't know if that's big enough. No, I should.
Yeah, that's good.
Okay, I should I'll try and go learn though. A subalgebra H of a Lie algebra G with bracket is, well, yeah, of course, what is a Lie algebra? It's a vector space with a bracket, so probably our subalgebra should be a subspace. Such that, well, we want it to be, of course, it should itself be a Lie algebra. Not only should it be some random Lie algebra, it should be closed specifically under the bracket inherited from G. So such that for all x and y in H, the bracket of x and y lands back in H. Yeah, exactly. The other big thing that we would like to try and understand, again, if we're copying things from groups and, well, many other algebraic structures as well, if you happen to study them, but groups, I think, is the common denominator amongst everyone in our group. We want to take a quotient, right? So the thing is, well, maybe Nestor, I'll ask you if you have any, if you tried figuring out what the condition on the quotient should be.
I think the condition is that it's similar to the kind of the subspace one, but instead of so we only have one x and h.
Yeah.
And it should be closed if y is in g, on the g being the bigger one.
Yes, exactly. And in fact, so how did you figure that out?
I'd read it before.
Oh, okay. So that's sort of cheating. So I want to explain it. I want to just take a minute to explain it this way. So we know, for example, in groups, we quotient by special subobjects, right? Normal subgroups. For rings, we take quotients by ideals, which are themselves not even rings, right? So we want to be open to the possibility that whatever we have is maybe not a Lie subalgebra. But okay, we want to take some sort of quotient. Well, again, we do have an underlying vector space structure, right? So just like even in the case of rings, where an ideal is itself not a ring, it's still a subgroup of the ring, right? There's an underlying, one way to define a ring is it's an abelian group under addition together with a multiplication operation such that blah, 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 right? And although an ideal is not a subring, it is still a sub-abelian group such that blah, 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 right? And so again, if we want to make sense of what the quotient structure should even be, well, probably H should at least be a subspace, right? Because then that's like, if we're going to take the quotient of a vector space, what are we going to take the quotient by? We're going to take the quotient by a subspace. right? So we should definitely be quotienting by subspaces. And we want our quotient to be another instance of a Lie algebra, right? And so that means we want some sort of bracket on our quotient to be defined, so I write my cosets additively because this is a quotient of vector spaces, right? I want it to be the case, so here, because x and y are arbitrary coset representatives, they're arbitrary elements of G. And I want, I want to define some Lie bracket, right? Well, sort of the obvious thing that you try is you simply say, well, it's going to exactly be, I'm going to define my bracket on the quotient, so I'll use Q to differentiate between the quotient versus the bracket from G, right? Well, it's just sort of, it's the only thing you can possibly try, right? It's like, well, I've got these representatives, they live in G. I'll define it to be the equivalence class, the coset defined by that bracket of x and y, right? And the issue comes in, remember, this is exactly like, so how do you land on, I mean, maybe in your group theory course, they just told you, oh yeah, normal groups, well, no, that works, right? But I think a good thing to go through and exercise is to convince yourself, why is that the condition you need? And when you go through and try to verify the group axioms, everything's pretty much fine. The issue is the well-definedness, right? Because now we're defining this on equivalence classes, right? So whenever you're talking about things defined on equivalence classes, you need to make sure that it takes the value, same value for whatever representative you take, right? And the point is that if you, maybe I don't want to spend all our time talking about this. So maybe I'll just sort of go, okay, well, I've come this one, I'll finish it. So suppose that you have some Z that's a potentially different representative of this equivalence class, and some W that's a potentially different representative of the equivalence class Y. Then what would have to be true in order for these things to be equal? Well, from this, you would need the condition that xy plus h is equal to zw plus h. And I thought I wrote up a good did not put it in these notes here. Oh,
Don't we want to make one of them be fixed? Like have x, y, and then z, y? Then we can use the bilinearity to combine them.
Yeah. I think that's, yeah, so I think, yeah, what we want to do is say, we want to say something like Z is X plus H. And W is Y plus K. Right, and then in order to do this computation, in order to check that this is well defined, right? You check, so what is Z plus H, Y plus HQ. If we expand this out according to our definition, this should be Z Y plus H. And that should in turn be X plus H bracket Y plus H. And that in turn, like you said, by the bilinearity, we get XY plus hy plus, oh, sorry, there should be k here. Plus xk plus hk. Right. And if this, right, if this is going to be, remember, we want this to be equal to the bracket of x plus h and y plus h, right? Now that would be true. What could we do to force it to be true? Well, notice that it's sort of these three terms are getting in our way. If these three terms weren't here, right, or they, another way to say it, if these three terms belong to this coset, we would be done, right? This coset would be equal to this coset. So what could possibly make that true? Well, one thing is that, as Metzger pointed out, we want arbitrary elements on one side, and remember by our, we can always switch the order by a minus sign, so it doesn't really matter if you're talking about on the left or the right, unlike ideals of commutative rings. So what's going on here is, we can see here we have y, this is an arbitrary element of G, right? And H is something in H. Same thing here, we have an X as an arbitrary element of G, and K is just something in H, right? So what we want for the condition for a thing to be a quotient is we want it to be the case that, say, for all X in G, for all H in H, it should be the case that XH is back in H. So this is very much like, very similar to the condition of an ideal for rings. And we might sometimes as a shorthand write it like this. So we'll sort of, as a kind of abusive notation, we'll write the actual algebras here to say, pick anything from this algebra, pick anything from this algebra, take the bracket, it lands in this. Notice, however, in this last term also, this says that anything in H and K, if we demand that this is in H as well, then that finishes, right? That makes sure that all three of these terms live in there. But what is that condition? I mean, sort of compactly, I could write it like this. Well, that's just saying that our the bracket of H is closed. So in fact, we want it to be a Lie algebra as well. So if it satisfies both of these conditions, so if you have something that is a Lie subalgebra, but it also satisfies the stronger condition that it's closed on one entry of the bracket by inserting anything from G, then we call this an ideal. So it's a nice sort of marriage of these concepts, right? It looks very similar to the case of ideals for rings, but it actually is more so similar to that case, but also like the case of a normal subgroup. For groups, it is actually a particular kind of sub-object. Okay, so there's also so of course, one thing we can try and do, right? We talked about last time. I don't know if anyone proved the theorem, but at least I stated it and suggested you try and prove that every finite dimensional abelian Lie algebra, it's completely determined by its dimension, right? Up to isomorphism, there's a unique abelian Lie algebra of that dimension, right? So one thing we might want to do is cut out, we're trying, that's sort of uninteresting in some sense, right? Like we're trying to get at more interesting Lie algebras. One thing that we might want to do, and maybe we won't get to this till next time, but I want to point this out for that sort of extra document, I said that there's a maybe more detailed, low-level version of Fulton-Harris proof, because Fulton-Harris is talking about this wedge product, and they're getting kind of fancy and playing loose with the geometry of it. But so one thing we might want to do is try and like kill all of the abelianness, right? And study the resulting algebra, because the abelianness is sort of uninteresting to us, right? So one thing that we can do, or maybe I guess it's sort of the other way. It's killing off the non-abelian structure, right? So the commutator or derived subalgebra. So I mean, it's called the commutator subalgebra or the derived subalgebra. Well, sometimes it is just called the commutator. Well, normally you say commutator algebra. Derived subalgebra is the subspace or the subalgebra and so we either use a fancy D and a G here, or sometimes this using this bracket notation. Again, we'll use this, but what I mean is basically we take the span of all possible brackets X and Y, where X and Y are elements of G. And so, of course, those of you who've taken Algebra 2, you'll recognize this as similar to the derived subgroup, and then there's the derived composition series. A similar thing happens here, and it does connect, even though we're not really talking about the groups at this point. Of course, there is a correspondence between the derived subalgebras and the derived subgroups. Yeah. And the point of this, right? The point of this is that G. So I claim that not only is this a Lie subalgebra, but it's an ideal. So again, I'm going to leave that for you to prove that this is an ideal. It's a good exercise in working around the brackets. It's an ideal, and G mod this is the maximal abelian quotient. Hang on, I think I'm getting a spam phone call from Ontario. So what I mean by this is if you take this quotient and you think about it, the thing you quotient by is always the parts that you're killing off, right? So we're basically, when we take this quotient, we're identifying every possible bracket with 0, right? So the thing that we should get afterwards is going to be abelian, right? So we sort of we kill off all the interesting things, and not only that, but it's I guess the thing to convince yourself is this is going to be the biggest quotient you can possibly find, which is to say that another way to say it is this ideal is the smallest ideal that you can take, so that the quotient is abelian, right? Because think, what do you have to do? You have to ensure that you're killing absolutely every single bracket in order to make sure your quotient is abelian. Right? Well, the minimal possible way you can do this is just say, well, I'll kill exactly those brackets, right? And then your fourth, it needs to be a subspace. So you've got to take the span of it, and that's basically it. You could say, oh, non-trivial brackets, but you end up with the same thing. Okay, so I wanted to just point that out, because even though for these first examples we'll jump into, this isn't the case, but as you'll see as the analysis goes on, one of the things that we do for in our effort to try and classify Lie algebras of small dimension is we break it into cases on what is called the rank in both Fulton and Harris and this document. But really, when they say rank, right, they mean the dimension of this subalgebra, right? So in particular, note that if the dimension of the commutator subalgebra is 0, well, that's only possible, it's the span of all these products, or the span of all these brackets, right? And the only 0-dimensional subspace is just the trivial subspace, right? So in other words, if this had dimension 0, it would have to be the case that all of our brackets are the 0 vector. Well, if all of our brackets are the 0 vector, what does that mean about our Lie algebra?
What's abelian?
Yeah, it's abelian, right? So in some sense, this is kind of a measurement of how abelian or non-abelian our Lie algebra is, right? The closer this number is, like the largest this number could possibly be is just because it's a subalgebra of G, the largest it could possibly be is G itself, right? And that would only be the case when the commutator is equal to G. So in some sense, this is like as non-abelian as possible, right? There's nothing, like if you try to, you can't even get an abelian quotient, right? Because if this is this, then the smallest possible ideal you can take to get a quotient that's an abelian is this, but that was your whole Lie algebra. So it's so non-abelian, you can't even get a quotient out of it that's abelian. Yeah, that's probably too much ranting about that.
So will that only happen when like would the only brackets that are 0 be the ones with themselves? Or could you have a bit more than that and it still be the case?
Oh, you mean when this is equal to this?
Yeah.
No, you'll have very interesting structure. You can have all sorts of crazy brackets.
Okay.
Yeah. Yeah. Because remember, when these two things are equal, it's saying that the quotient is the only non-abelian thing. Or sorry, is when these two things are equal, it's very non-abelian. It's
Right.
very non-abelian. So you're gonna have relative chaos. Well, we're gonna see there's some very nice examples of this that we'll get to eventually. In fact, at the very, I don't know if I'm gonna go through absolutely every step of this classification, but the point is, well, the end of the classification, the final one that we see has this property, and in fact, it's what I consider to be the single most important Lie. Somehow I don't feel confident saying this about groups, like there's no group I can think of that I'm like, this one group is the most important group. But in Lie algebras, there's one that really is the most important, I think. Yeah. So now we'll start trying to classify the small dimensional Lie algebras, or maybe continue because we did sort of start last time. And what to say. And the point is, well, yeah, it's sort of nice and ugly at the same time. it's nice because I think like we're really going to you know, if you looked at the notes that I posted yesterday, there's talk about diagonalizing matrices and you know, we're really gonna get down into the trenches of playing around with brackets and bases and talking about diagonalization matrices. We're really gonna flex our linear algebra skills. And I think there's some really cool, there's something I want to say about the word moduli space, which is kind of fancy, but secretly one of the answers to the questions gives us like an example of a force moduli space. So I'll explain that when we get there. So it's really nice in that sense, but it's also kind of, you know, as we go through all of this, you see along the document is like, gosh, how are we gonna gather together all of these Lie algebras? It seems like this very sort of hodgepodge, mishmash set of techniques to try and classify them. But I'm almost so it's kind of gross in that sense, but it's like in the way that, you know, when we teach you about integrals, we first make you do a bunch of Riemann sums, right? Which is kind of a nightmare, even for basic functions. And then we give you this beautiful theorem, the fundamental theorem of calculus. And wow, what an amazing, like, magical thing that is to use to compute areas compared to Riemann sums, right? So in the same way, it turns out that at least for the complex semi-simple Lie algebras, which are essentially building blocks in a way that we'll make more precise, of the other Lie algebras, has just probably one of the most beautiful classification theorems in all of mathematics. It's just the right mix of complication and simplicity, right? Like, yeah, sometimes things are just too complicated, right, to have a nice classification theorem. Sometimes they're too simple, right? Vector spaces, it's too simple. Yeah, there's one of each dimension, one for each cardinal number, great, you know. But this is just the right mix. Okay, you probably want to see some math and don't want me to just wax philosophical the whole time. I guess actually the better thing to do, we'll get into classification, but the better thing to do is maybe prepare you a bit more to do some more reading from those notes on your own. So one thing, maybe another question to ask you related to the homework is, how do we put, right, because we talked about this idea of analysis and synthesis, right? So now I know that I can find like subspaces and substructures that can help me carry out this analysis, right? And I know that I can take quotients of certain things, and so that can help me deconstruct my Lie algebra and break it down into simpler parts and sort of think about those cases separately. What if I wanted to put my pieces of the algebras back together again? What are some ways I can glue the algebras together to obtain new ones?
Take the direct sum, maybe.
Aha! But what should that mean? What should that mean? I mean, those of you who speak some category theory, you have the advantage of a very general definition of direct sum. And so it's a good exercise. Go through the universal, universal, what is the word? Why am I blanking on the word now? Universal, the limit construct, the universal definition of coproducts in a category, and you'll be led naturally from the universal property of coproduct. But we don't have to be so fancy, right? We can just sort of guess what this has to be, again, based on the information we have. So Aiden, what should our definition of a direct sum? So given Lie algebras G, and I'll denote its bracket with a sub G, and H, the direct sum is what?
Well, the vector space should be just the direct sum of G and H as vector spaces, but then with the
Exactly.
bracket, I mean, obviously it's easy to see what's going to happen on the sort of like G part and on the H part alone, but on the kind of where they're coming together, I'm not entirely sure.
So yeah, you're definitely right about the first part, right? I mean, just like every other thing we've talked about, we know that we have an underlying vector space structure. So is, you know, the vector space G direct sum H, right? So that would be our underlying vector space, exactly. With bracket, just to be really pedantic in my notation, I mean, normally we drop all these symbols, but I'll even put like a little, you know, plus thing down there, defined by for all, well, I need to take pairs of elements in G direct sum H, right? So this will be X and Z and Y and W, and this is in GH, right? So remember that our sort of the standard way that we, you know, give an explicit construction of the direct sum, say, of vector spaces, is it's actually just a subset of the Cartesian product, but in which, you know, we impose linearity separately in each factor. Right, so that's like AUV plus BV, comma, CW, for example, we say that this is going to be like AUW plus BVW. Oh no, sorry, I'm confusing that with bilinearity. Right, that is not right, that is not the case. Sorry. We say that U V, you know, we define this UV W X, right? We define that to be this thing. And then similar thing with scalar. The scalar comes in and hits both of those vectors, right? So alpha UV, we define that to be alpha U. Okay. So what should we do? Well, okay, I have a pair X and Z here, and I have a pair Y and W, and I need to decide, I'm going to send that to some pair of elements, right? Because it's going to be back in here.
Just take the bracket in G and the bracket in H separately, like the bracket of X and Y and the bracket of Z.
Exactly. And thematically, this makes a lot of sense too, right? Because like when we take the direct sum of the vector spaces, those are normally like orthogonal to each other, right? We imagine those spaces, well, I mean, okay, it doesn't make sense to talk about orthogonality in the absence of an inner product, but that's normally how we think about the direct sum, at least for Rn, right? If you take the direct sum, like these vector spaces are sort of as distinct from each other as possible. So it makes sense that really the two Lie brackets aren't really going to have anything to do with each other, right? So I don't know how legible that is. So yeah, I'll just take the two things that belong in X, or the two things that belong to G, combine them with the bracket that combines things in G, that'll go in the first slot. Take the two things that belong in H and combine them, and that'll go in the second slot. Yeah. Yeah.
Is there a way to know if we have a Lie algebra, like are there any conditions to check in which we can decompose it into different like direct products of other algebras?
Good question. Good question. Yeah, so that's the thing. I mean, related to this is the idea that you know, for vector spaces, we can always compose things as direct sums, right? You just find a subspace and yeah, work your magic. At least if you've got the well, they always up to isomorphism, you know, you can always decompose things as direct sums into any subspaces you want. Or sorry, not any subspaces, but it is always isomorphic to a direct sum of at least if you have a finite dimensional vector space, you pick a basis, you can use that to show that it's isomorphic to just a direct sum of the one dimensional, right? So this is actually a concept that comes up a lot. It's sort of to be very fancy. The idea is that we have simple objects, and in our you know, simple objects, and we want to decompose our larger objects into these simple ones, right? So, for example, in group theory, we have what are called simple groups. Right? Those are the simple objects. Those are the groups that have no non-trivial normal subgroups, right? And you might hope, right? So in vector spaces, it's pretty nice. Like complex vector spaces are all just isomorphic. There's exactly one simple object in vector spaces. In say finite dimensional complex vector spaces. That's what complex numbers is. Everything decomposes as up to isomorphism as this direct sum, right? For groups, you know, the sort of hope that you might find is, oh, let's figure out what the simple groups are, and then every group should just be a product of whatever these simple groups are, right? Thing is, life is not so nice. It turns out that you can have groups that are somehow glued together out of pieces in ways that are just more complicated than the direct product. So some words to look up if you're curious. For those that don't already know, there's things like the idea of a short exact sequence is exactly what allows us to glue, say, two simple groups together into a larger group in a way that's more complicated than the direct product. Okay, if that's too fancy for you, there's also the concept of a semi-direct product. So that might be more understandable to look up. And I really do, you know, I've got a thesis to write at some point, but I really do want to make some videos explaining why the definition of the semi-direct product is the way it is. There is a good explanation, but if you just go look at it on Wikipedia, you'll be like, yeah, okay, I guess that defines a group, but there's a really good explanation as to why that is. So great question. And maybe let me just give you one more example. Just because some people might know about representations. Even if you don't, I think based on what I just said, you can probably appreciate the statement is that, you know, there's a notion of irreducible representations. These are exactly you know, in the study of representation theory, the simple objects, right? They don't have, there are simply no sub-representations of them, right? So that's what it means to be an irreducible representation. And it turns out if G is finite, then any representation over the complex numbers is a direct sum of irreducible representation. Very much not true for fields of characteristic P or for infinite groups. So again, yeah. So this is an important question, and here we see, you know, even though maybe you don't have experience with some of the examples I just brought up, but we see that there's a variety of different things can happen across different fields of algebra. Sometimes everything's decomposable into simples, and the simples are really sort of dumb and stupid. Other times, even classifying the simples are difficult, and then not only that, the ways that those simples can be glued together into more complicated objects is just chaos. Yeah. So I mean, that doesn't really answer your question, what's the case for Lie algebras, right? But I sort of want to paint this picture, and there's a little bit of a clue in some of the things we've already talked about, right? So I mentioned that one thing we might aim for is the classification of semi-simple Lie algebras. Okay. And we have seen examples of quotients. Yeah, the question is, can everything be decomposed? Can everything be decomposed as a direct sum? And maybe this is one point where, again, I don't want to stray into the Lie group theory yet, although if we as a group collectively decide, you know what, we want to go there instead and learn manifolds, okay, we can. But one of the utilities of Lie algebras is that there's a correspondence between Lie groups and Lie algebras, right? And well, who knows? I mean, we could say, well, for groups, even for finite groups, we know the situation is much more complicated than just direct sums. But Lie groups have some special extra structure, right? They're manifold, so maybe that rigidity helps save you from this sort of complicated thing. So I'm deliberately not answering the question by just showing you flavors of how this question comes up in other areas. And so I would encourage you to maybe look at it. Well, I would encourage you to think about it a bit on your own, and also think about it as we go through this classification. So, I mean, the answer might be spoiled. You might spoil it for yourself in this process, but I don't have the precise reference, but in Fulton-Harris, they do define, in the section before this classification stuff that I wanted to talk about, and then, you know, I always get sidetracked. They do define, where they define the commutator, they define the derived series, they define ideals, they define solvable algebras, subalgebras, all of these things. They define, I think, both simple and semi-simple there. So I would at least find the definitions of simple and semi-simple, and then look at our classification, like start going through the classification where I have, you know, that nicer document I posted with more details. And as examples pop up where we say, oh, this is this Lie algebra, this is this Lie algebra, ask yourself, can this one be decomposed into a direct sum of simple Lie algebra? Or better yet, can you find an example where you have a Lie algebra G, which itself is not simple, and not the direct sum of symbols? I mean, the fact that I'm asking you this question, is kind of an answer unto itself. So let me, in the last 10 minutes, yeah, I guess we'll just make going through part of the classification homework, and then there's just a couple parts that next week I really want to talk about together. A couple of key examples I want to talk about together. So the last thing that you'll need to know for this that I want to explain a bit is well, one of the things that's really important, for example, in the study of group theory is conjugation, right? So we have some group G, and remember that if I have an elements G and X in G, I can conjugate X, which means I multiply on the left by G and I multiply on the right by G in, right? And a big thing, so for those of you who have taken algebra 2, recall that this actually gives us an action of the group G on itself, right? So, and this also leads to the study of conjugacy classes. And this is a really useful tool for understanding the structure of a group, right? We can look at a group, we can sort of see how this group shuffles elements around on itself, right? How you can use this group to sort of push elements, its own elements around. In particular, right? Remember the property of being a normal subgroup, right, is exactly that G and G inverse is contained in G for all G in here. In other words, it's normal if for every element, if any n in n, and for any G in G, if you were to conjugate n by G, you would get something back in n, right? So it's closed under conjugation. Well, a similar thing happens in Lie algebras. So one of the things that we have a couple operations on a group, right? So we can define various different, so like there's bijections. I can define a bijection from G to G, which I'll call LG, right? So for every L in here, I can define a function from G to G. And what does that do? I'm going to eth an element X, and I'm just going to multiply on the left by G, right? So for instance, that's a bijection. And this bijection tells you something about like the left cosets under G, right? If you restrict this to say normal sum. But that bijection is not a group homomorphism. It'd be nicer if we had a group homomorphism, right? So that's another thing where conjugation comes in. So sometimes we might write this as psi sub G. Now, that's awesome because not only do we have this idea of conjugating elements, we actually have an automorphism of our group, right? And that automorphism, right, it takes an element of G and it sends it to this conjugate by little g, right? And so actually studying we can study the elements of our group themselves by studying these homomorphisms. And that's, that can be nice if we have certain structural theorems about homomorphisms. So applying the same philosophy to Lie algebras, recall that the Lie bracket is bilinear. One way to say what this means is that given any element of my Lie algebra, if I fix the first coordinate, right? So I can define a map, I'm going to call it add of x, it's called the adjoint map. So it's going to go from G to G, and what it's going to do, it's going to take an element y, and it's going to send it to x bracket y, right? So I'm just fixing the first term in this bracket. But that means that it's linear in this second coordinate, right? If I have right, add x of a y plus b z is going to be just x of a y plus b z bracket, but by the bilinearity of this bracket, that is axy plus bxz. And so that is a times add of x applied to y plus b times add of x applied to z. That's exactly what it means to be a linear map of vector spaces, right? Well, holy crap! The thing I said, right, is the only thing we understand is linear algebra. And now we've taken some part of our Lie algebra, we've turned it into a linear transformation on the underlying vector space. That's amazing, because now we can do stuff like we can talk about that linear transformation as a matrix. We can talk about that linear transformation, we can ask about its eigenvalues, determinant, and its rank and its column space, all these sorts of things, right? And now we can take the tools of linear algebra and start to use that to study these elements and these maps and how they act on our Lie algebra. This is, I think, even more amazing than the concept of conjugation on a group, because conjugation on a group is awesome because somehow the group is pulling itself up by its own bootstraps, right? We have this way of the group acting on its own internal structure. Here we get the same thing, but with the double bonus plus of the fact that now we have a linear transformation, right? And so now we can bring all the tools of linear algebra. And this is such like, this thing comes up, so we're gonna see it's useful for us now in this document when we get it, when you get to the three-dimensional Lie algebra stuff, and it's going to play an essential role in the very beautiful classification theorem. This is sometimes called the adjoint map or the adjoint representation. Okay, and that's basically puts us at an hour, which is awesome. So I think yeah, I'll probably say this in the Discord, but for next week, I guess let's just on our own, let's try and go through that classification as much as you can, and then I think probably what I'll do is just, yeah, like I said, highlight a few key examples from that classification, and we'll take it from there. We'll figure out what we want to do after that. Yeah. Any questions?
Will we ever come back to like solvable Lie algebras and stuff like that, or?
Probably. Yeah, I guess it depends, but yeah, they'll probably come up again. Yeah. But I'd also encourage you, so like there's some people who have mentioned they have particular interests, and I mentioned, and I said, hey, maybe, as an extra side project for yourself, if you feel that that's what you want to work on, we have some people interested in algebraic topology, there's connections here, some people interested in physics, and then maybe down the road, once we have these basics down, those people can give presentations on those things. So if we don't cover solvability to your liking, then maybe one of the things you can do is dig deeper into it and like give a presentation on it at a later date.
Cool.
Yeah. Yeah, okay. I guess I'll end the recording there.
We're doing a new poll for a new time next week, right?
Yes, there is a new poll. I just want